Hi, hello everyone. I'm Yuyou. I'm from University of Utah, and my advisor is John Regier. Today, I want to introduce our project, Alive-mutate. So it's a fuzzer that cooperates with Alive2 to find LLVM bugs. Let's start with testing. So there are two important problems in testing. The first is writing a good test case. The other is knowing what each test case should do. The diagram below is a typical workflow of LLVM late. So it starts with IR file, sends into opt, and opt generates an optimized file, sends to file check, and our file check returns a result. Let's start with a real example. So this is a test case I took it from insta-combine pass. So it's a file name canonicalized clump like pattern between negative, positive threshold, something. And we don't need to get into that, but we can just have a quick glance on this function. It has constant, negative 16, positive 16, and 144. It has instructions, I comparison, selection, add, and other comparison and selection. So I'll use this example to explain the 2 points I mentioned before. Is it a good test case? Yes, it should be, because it's in the repository, and it's reviewed by many people, and it matches the specification. Do we know what does this test case do? Yes. From its file name, we can know it's canonicalized some pattern, and the pattern is defined in the source file. We may not get the detail of what exactly it does, but we have a rough idea. Now, I'll do a slight mutate on this test case. So here, you can see I changed the constant from there's no more 16, negative 16, but it's 0, 65, 36. And there is no add instruction, but a XOR. So it's just for easy to understand, I write the select language code on the right. So basically, this code does if checks if x larger than 65536, return x. Else if x is less than 0, return low, else return high. Because this test case is in the insta-combine path, let's call insta-combine with it. So after calling opt with insta-combine, the thing changed a little bit. In the optimized code, we only got 4 instructions. It starts with 2 comparison and 2 selection. The code is still right on the right. So basically, the checks if x is larger than the 5-digit number, return high. Else if x less than 0, return low, else return x. The reason I want to show the example here is the optimization on this mutated test case is actually wrong. Let's see. So consider both functions with input. X equals to 2, low equals to 0, high equals to 1. So let's see before optimization. If x, which is 2, larger than the 5-digit number, no. X less than 0, no. Else return high. So before optimization, it returns 1. Let's see after optimization. If x larger than the 5-digit number, no. X less than 0, no. It return x, which is 2. So the same function before and after optimization for the same input gives different answer, which says our transformation is wrong. So from this example, we can see 2 things. The first is our developer wrote the right test cases, but not quite. The second is we need a test oracle to tell us the correctness of this mutated test case rather than human inspect on it. We can do better on the second things. So Alive2 serves as a test oracle. It provides a refinement check for LLVM IR transformations. The image on the right is an example output from Alive2. The input is the example we took before. It checks if the transformation is invalid, it will give us a counterexample. So here is x equals to 2, low equals to 0, high equals to 1. And it will print out all the values in both source and target function. By using Alive2, programmers can be more clear about what a test case should do. If we adopt Alive2 in our workflow, it should be like this. We start with an IR file, send it to opt. Opt generates an optimized IR file. Besides, IR file also send into Alive2 directly. Alive2 receives both and give us a result. Now, can we do better on the first problem, which is get a more good test case? Yes. If a test case have found bug before, a modified version of it should also be a good test case because of defect clustering. The LLVM repository have so many good test cases, so we can use them to generate more for saving people's effort. As a result, we can build a mutation engine to do such things. Here comes Alive-mutate. Alive-mutate is a tool that cooperates with Alive2. So the workflow diagram on the bottom, so we start with an LLVM unit test. After mutation engine, we got a mutated test and send it into opt, basically typically with O2 option, and we got an optimized test. Both of them are sent into Alive2. Alive2 will report the result if it's correct transformation or timeout, or it is a compiler bug. Next, I'll introduce what the mutations we have and our key features. So basically, we organize our mutations into 3 levels: functions, basic block, and instructions. We maintain 3 iterators pointing to each level. So we only perform 1 mutation to 1 level at a time. For example, we will do a mutation on function first and report this test case. And we'll do mutation on a basic block and report it. Finally, we will mutate a instruction inside the basic block and report it. We have 2 advantages by this method. The first is it's easy to add or disable some mutations we want or we don't. Another is we always generate valid IRs, thus we can maintain a high throughput. I'll start introduce mutations from function level. Here, this is our first mutation. We can set or unset attributes of a function and its argument. So here is a function signature. It has function name t. It receives 3 parameters. 2 of them are i64 integer, and the last one is a pointer to i64 integer. It returns i1. In the mutated version, we add a sign extension to the return result as well as the second parameter. And we add no capture and dereferenceable to the pointer parameter. Finally, we added no free attribute to this whole function. If we add it, we can also remove it if you originally have those attributes. Next is a mutation about basic block. Here, I give the detail of function t. Function t consists of 4 instructions. There is no dependencies between these 4 instructions. So we can change the order arbitrarily without worrying about validity. Here, we have a 1, 2, 3, 4 instruction, and we can change the order to 4, 3, 1, 2. It is still a valid IR, because we don't need to worry about the dependencies. But what if we need to worry about the dependencies? Here comes another mutation. We can move an instruction around. So basically, we want to move v2 around. We can move it forward or backward. Here, we move it forward before v1. However, in this example, v2 has an dependencies from v2 to v1. So we first move it, and then we solve the data dependencies. One solution to this is we can add a new function argument and change the usage from v1 to the new added argument. This is what we did here. We add a new function argument arg2 with type i64, and we change from v1 to this new added argument. Of course, we can have other solutions. Here, another mutation is called replace operand to others. In this example, we add a new instruction called new. New is an AND operation between v1 and a random generated number, and we changed the function usage from this v1 to this new instruction. Besides, we have a special mutation on binary operators. Because binary operators are almost predefined, and they only got 2 operand. So we can do maybe a, say, swap operand, change the operator, and add a certain flag on it. Here is the example on v2. v2 is a arithmetic shift and has operand v1 and 23. In the mutated version, we change it to logic shift and add an exact flag on it, and change the order from v1 23 to 23 v1. Finally, we have a mutation called change the width of integer definition. This mutation is really important to backend because we use it to find many backend bugs. So here, v2 has type i64. We want to change it to type i8. So there are 3 steps. First, we need to truncate both operand. It's in the code on the right, there's instructions 3 and 4. There's truncate instruction to v1 and 23 from i64 to i8. Next, there's a new v2, just to do the arithmetic shift on the new operand. Finally, we need to solve the data dependence. Here in instruction v3 and v4, they use v2, so we add a last instruction here to do an extension from i8 to i64 and change the usage from old v2 to this last instruction. Finally, we have two more mutations related to functions. The first is inline function call. Here is a function f. It has a function call to the t, to the example we took just now. So we can just inline it with v1, v2, v3, and v4. Actually, we can inline any function in the module with matching signatures. That's how we implemented it in the real project. The other is simple. If it's a call to void function, and we can just remove it. Next, I'll show our experiment result. We have found 29 bugs so far in LLVM. We divided the bugs into 3 categories: 19 bugs generating wrong code, 9 bugs causing crashes, and 1 test file is originally wrong. So I picked the 2 typical bugs here. The left part is about generating wrong code. We found 10 bugs in ARM64 backend, and most of them have simple form. For example, this function receives I1 integer and returns I64. The first operation is do an extension, and the second is do a logic shift and return it. It miscompiles due to global instruction selection. And on the right part, it's about crash bugs. We found 5 related to insta combine paths. For example, here is a function receives I8 integer, returns I8 integer. First, we do an add operation, and we do an smax with the added result with a negative 124. Return it. It causes a crash. And this is my end of my presentation. Thanks for listening.
Thank you. And thank you for catching those bugs in the code generation. It's much appreciated. Questions, please.
Hey, thanks for the talk. When you modify your test cases, can it happen that you generate, inputs that are kind of that now contain undefined behavior, and if so, does that matter?
Yes, because Alive2, we first generate a test case and send it to Alive2. Alive2 can solve most. Alive2 will report, Alive2 doesn't work well on the undefined behavior, so we might skip those test cases.
Okay, so it will check.
Yes.
Oh, you did this, and then you say, oh no, if I did this, I don't use that test case.
Another thing is we will particularly skip undefined behaviors, such as introduce undefined in our code.
Okay, okay, fair. And then, I forgot my second question.
Hi. So I feel like I kind of missed something. So you're using Alive2, and that's going to find errors in opt, but then a bunch of the issues that you found were in the backend. So if you're mutating the IR, how do you know what the right behavior is to detect a miscompile in the backend as opposed to a crash?
Mm-hmm. In fact, about backend bugs, so there is another talk. It's by Nether. He also has a tool to, my tool cooperate with his tool to find the backend bugs.
Okay. Okay, thanks.
A quick one. So you have these test cases, and your argument was the existing test cases are cool because of clustering of errors, right?
Yes.
But then you take the test case and you mutate it, but then you run O2 on it, which is very likely a different pass pipeline than the original test case was run on. Why not keep the passes that the original test case was run on? Because if you run O2, the first inst combine or simplify CFG might delete all of it, and then you never actually test stuff at the end of the pipeline.
Got it. So I'm not sure if I understand your question correctly, but all the mutations for now is only concerning data flow. We don't do mutations on control flow.
No, I mean, the test you grab from the test suite has a run line that specifies what passes to run, in what order. Why replace that with O2?
So we can implement that as well, because the diagram, we send the test case by opt, and there's typically O2 option, right? We also support other passes. So you can just, there's a parameter, you can just set the parameter and it will execute it.
Oh yeah, so you could keep the original pass. passes.
Yes, yes.
Thank you.
Yes, we also found a bug in new GVN as well, new GVN pass.
Right.
Thank you very much.